Hi. In this lesson, we need to move on a little bit in looking at how geology can affect the engineering of major structures. And in particular, for us to think about dams. But first, we need to look at some of the answers uh, on the exercise we're working on the channel tunnel. So we're working on pages 20, 21 and 22 of our Theme 13 booklets. Okay, let's go. Okay, to start with, let's just quickly go through some answers for the channel tunnel activity you were working on in the last lesson. First question, how deep is the deepest part of the tunnel? And that's actually about 75 meters below the seabed, not sea level, below the seabed. Now, the channel tunnel benefits from the geology because most of the tunnel is actually following the same bed through a fold, through a synform. It does mean that the engineers could actually follow that one bed. They actually used the fossils that were in it to trace their route through that bed. And it brings them most of the way to France. Now, there are some other geological structures that can affect this. The faults. Some of them on the English side, but in particular, underneath the seabed on the French side. And they can be an issue because they could be a pathway for water to get down into the rocks around the tunnel. That could be cause some problems, both of seepage into the tunnel and also swelling of these clays. Okay. Now, most of the way, the channel tunnel is cut through the chalk marl. Advantages of that are it's impermeable. It's clay, so that's going to minimize the amount of water getting in most places. But if you look at the French end there, you'll see that the tunnel actually comes back to the surface through the chalk because there is an antiform there that takes the chalk marl deeper below the French coast, so the tunnel had to leave it behind. The downside of using, or the downside of the material underneath, is this clay. The gold clay is going to be weak. It's incompetent. It can deform, especially with the stress on it. It can shrink if water's taken out. It can swell if water gets in there. The gold clay, clay in general, is terrible stuff to build on. Okay, let's move on. Let's think about dams. I've got 4 cross sections through different styles of dam here. We have different dams built in places that have different geology. So what I want us to do is I want us to look at each of these dams and think about the type of geology that they'd be built on. Because each of these dams has a particular reason why it's built. All of them are, though, designed to be walls that block off a valley to be able to store water behind it. To be able to do that, though, the force of that water going down the valley has to be taken by the dam and has to be spread into the rocks that the dam is built on. Each of these dams do that in a slightly different way. Let me explain. This is actually a picture of the Hoover Dam in Nevada in the USA. This dam is a type of dam called an arch dam. You can see that from the shape of it. It's a curved shape. It's a very strong shape. And what that arch does is it takes the stress of the water pushing down the valley and distributes it onto the rocks either side. Now, you can only build these dams where we've got a narrow valley. It doesn't work on a very broad valley. And also the surrounding bedrock has got to be really quite strong, because the dam itself isn't really taking any of the weight itself. It's just transferring that force into the surrounding rocks. This is our second type of dam. This is called a gravity dam. And this is a big, thick concrete wall. It's big, it's heavy, it's very strong. So this one is far more about the size and weight of the dam resisting the force of the water. And they're made of one huge block of concrete. As a result, they are quite expensive. There's a lot of materials that need to go into these. They are quite heavy, but they've got a reasonably big footprint as well, so that the stress of that dam is spread over a fairly wide area. This type of dam, this is actually a picture of a dam in mid Wales called Nantamor. This is what we call a buttress dam. And it works in a similar way to a concrete gravity dam, except you'll see that there are, if you like, big scoops taken out the front of it. That reduces the amount of material needed to build the dam. And what we have here is the force of the water then is taken by these buttresses, these like arms of concrete projecting out from the dam. This means, though, that although it uses less material, there's more force that goes onto the bedrock. So the bedrock for a buttress dam needs to be stronger than it would be for a concrete gravity dam. And the final type of dam is probably the lowest tech of all. This is what we call an embankment dam. Here we have a central wall. You can see on this particular one there's a road built across it. And that wall is supported by a mound of loose rock and soil piled up either side to make this sort of large triangular shape. This type of dam has the biggest footprint of all, uses a lot of materials, but because it has such a big footprint, it can be built on very weak rock. Quite a few of the dams, for example, in the Brecon Beacons, are embankment dams because of the weak sandstones and shales that make up the mountains. Okay, these can be built though across quite broad valleys. There's a limit though really to how high they can go. If they start going very high, the amount of material that's required is enormous. Okay, so we should in that have been able to complete question 13. What I'd like you to do now is to start to think about question 14, where we start putting all of this together. I'd like you, using this map and the cross sections that go with it, to identify engineering geology problems. What issues could there be building this road across this area? You'll see plenty of clues on the map. See if you can identify them. Circle the ones you can identify, number them up, and then I'd like you to identify the problem and see if you can come up with a solution to that particular problem. Okay, so press pause now and have a go at that. See what you can come up with. Okay then. Now, I'm not going to give you the answers to this, but what I'm going to do, if you're not quite sure where we should be starting with this, I'm going to give you some places to look at. So these are the places where I've identified problems. Starting from the south, we've got some issues there and there. What's going on with the river? There, coming off Grey Peak. We've got an issue there by the dam. What's going on with the dam itself? Have a look at the cross section, see if we can work that out. Got a similar issue on the other side of the dam as well. What's going on there with the river and the road? And perhaps even something that's going on underneath that bold ridge. What's actually making that? So we've got lots of different potential problems here. Can you identify what problems there are there and what solutions that you would come up with for those problems? See what you can come up with. We'll talk about the answers next lesson. As we see the sunset over the Hoover Dam, we can see that the geology has a significant impact on the construction of major engineering projects. Tunnels and dams are perhaps the most extreme end of this. It's really important to get the geology right so that you can engineer solutions for any issues that the geology throws up. Next time, we'll start to wrap up theme 13. I'll see you then.